Welcome to Chemical Process Safety. This video is about flow of liquids through pipes. So last video, we talked about flow of liquids through a hole in a tank. And in this video, we're going to extend the logic to flow of liquids through pipes. And this is a fundamentally different situation because whenever a fluid is flowing through a pipe, there's some pressure that is applied to get the liquid to flow. And a tank, for example, is just sitting there. So there is no pressure being applied. And the only pressure that comes about because of the liquid being in the tank is either due to hydrostatic pressure or if the tank is stored under pressure or something like that. So once again, we'll start by performing the mechanical energy balance. So just starting with the same form that we have been. Once again, the liquid is incompressible. So P1 minus P2 over rho, the delta P term instead of the differential. And one of the big differences for flow of liquids through pipes is that we could be more descriptive about the friction factor F. We don't have to keep doing the discharge coefficient C0, C1 thing. So we can express the friction factor as Kf times this term, the average velocity squared, over 2 times Gc. Remember, this is the gravitational constant. That is 1 for SI units and equal to 32.17 for US customary system units. This Kf term is called the excess head loss due to the pipe or the fitting. There's a table that's going to be in the textbook that is going to help us with this. If we're talking about a pipe, we've got this expression Kf is equal to 4 times little f times L over D. So the terms in this equation are little f is the fanning friction factor, which should be familiar to you from physics class. L is going to be the length of the pipe, and D is going to be the diameter of the pipe. Once again, units are going to be important, but we'll talk about that a little bit later. Now, for laminar flow, we have the expression that little f, the fanning friction factor, is equal to 16 over the Reynolds number. And for chemical engineering industry, we are not going to see this situation very often because many flows, especially at large scale, are going to be turbulent. So we won't see this very often. Unfortunately for us, that means the turbulent flow situation is a little bit more difficult. So we have to use the empirical relationship. This is figure 4.7 in the Crowell-Luvar textbook, which I'll pull up in just a second. For any Reynolds number that is very large, the fanning friction factor is independent. So one example that we can use is the Colebrook equation, which is listed here. Sorry about that, and I realized I was missing a term here. So there's a Reynolds number times the square root of the friction factor. So again, the Colebrook equation is empirical, so the 1.255 looks a little bit odd. That number doesn't come from any sort of theory. That comes from being fit. So somebody performed an experiment and determined that this number gave the best fit. So going back to what I was talking about over here, for a large Reynolds number, the friction factor is going to be independent of that Reynolds number. So what that means is if the Reynolds number is sufficiently large, this entire term, this 1.255 over the Reynolds number times the square root of the friction factor, that is going to be approximately 0. Like imagine Reynolds number was like, 100,000 or something like that. 1 divided by something that's 100,000, even though it's being multiplied by the square root of the friction factor, is going to be very, very small. So we can simplify this expression into this one. This is for fully developed flow at large Reynolds number. Notice that this is the same equation just without this Reynolds number dependence. And this is actually very helpful because if you notice in the unsimplified version, imagine that we wanted to solve for F with this equation. If we knew the Reynolds number, if we knew epsilon, by the way, this is the pipe roughness, which I don't think I've mentioned yet. D is again the pipe diameter. How would we solve for F given the Reynolds number? Well, the only way that we could do it would be iteration if we were solving by hand, or we would have to plug it into Excel or something. This would not be a simple plug and chug type exercise because you cannot isolate the friction factor. That is not the case with this form of the equation. There is no square root of F or F on the right-hand side. So this you can just plug into your calculator. It's a lot more simple. Let's look at what this equation looks like graphically. So this is a plot of the fanning friction factor little f on the y-axis versus Reynolds number on the x-axis. This is a logarithmic plot, meaning that the scaling is going by 10 to the power of something. So this, as you go further out on the x-axis, you're becoming more and more turbulent. So notice that again for laminar flow, where the Reynolds number is below a certain value, we have a linear form of the friction factor, which is equal to 16 divided by the Reynolds number. And then once we get turbulent, we follow these curves. And these different curves correspond to different relative roughnesses. So this plot is a little bit difficult to read, but let's say the relative roughness was 0.004. We'd be looking at this line. We would go to whatever the Reynolds number would be, and then we would read the friction factor based on wherever the curve is, and that's how this plot would work. It's personal preference, whichever one you find easier. If you want to use this chart, you can simply use the chart, or if you'd like to use the equation, whichever you find easier to use. By the way, the fact that these lines become horizontal as you go out, that is signifying that for large Reynolds number, again, the friction factor is independent of that Reynolds number. So that's what the fact that they become horizontal is what bears that fact out. So that's all for flow just in pipes. Now, if you've gone to an internship or a chemical plant or something, you know that you're never going to find just a long pipe. There's going to be all sorts of fittings in that piping network. So that could be a T intersection, a valve, an elbow, anything that is not a straight length of pipe segment would be classified as a fitting. And fittings introduce additional friction loss terms. So for this, we're going to use the 2K method. This is an alternative to what they call the equivalent length method. And how you do this is you define a term, Kf. This is, again, your friction, equals to K1 over Reynolds number plus K infinity times the quantity 1 over the inner diameter in inches. There's a table in your book, table 4.2 has K1 and K infinity parameters. Depending on which type of fitting you're looking at, different fittings will have different parameters. So you'd simply plug those in, you would know what the Reynolds number is, and you'd also have to know what the inner diameter in inches specifically are. That's, again, an important unit distinction that we have to make, is that you have to convert, if you're in metric, to inches, because the K1 and the K infinities that are going to be in the table are going to be based off of inches. So a little bit annoying, but it's what we have to work with. And definitely something you should get used to, especially if you want to work in the United States, where a lot of the equipment is going to be in the US customary system. For pipe entrances and exits, this is a special case. So for a normal entrance, we've got K1 is 160, K infinity is 0.5. For a boarded type entrance, which is where there's an entrance to the pipe that kind of dips into a liquid level, we've got a different value for K infinity, and for a pipe exit, we have different values for K1. All right, so how would we go about solving a problem involving a discharge from a piping system? So this would be a case, for example, where there's not just a hole in the pipe, but let's say the entire pipe gets sheared off at some point, and we've just got chemical that is being lost from an entirely disconnected section of pipe. So what we need to know is the geometries and the types of pipes. So by geometry, I mean, is it 4 feet of straight pipe segment, an elbow, another 2 feet of pipe segment, a ball valve, and then another 3 feet of pipe segment? That would be one example. And type of pipe means stainless steel or carbon steel. That's going to have a different roughness. We need to know the number of fittings. So I kind of mentioned that earlier with the number of valves, elbows, T's, etc. Fluid properties, meaning the viscosity of the fluid, the density of the fluid, and other givens that you need for the energy balance. You then determine 2 points for which you'll take your mechanical energy balance. That's not too different from what we've been doing so far. We would then determine the pressure at both points. And again, since we're talking about a piping network, 1 point, I'll give you the flash forward. 1 point definitely has to be the point of discharge. And then the other point is going to be some point where you know the pressure. So commonly what you'll see would be, if you know the pressure, the discharge pressure for a pump, for example, that would be a good point to take your P1 for the energy balance. Or if the pipe was coming from a storage tank where you know the pressure. Somewhere where you know the pressure has to be your 0.1. You would guess a value for the average velocity at 0.2 unless you expect fully developed turbulent flow. And the reason why you have to guess is because this is an iterative process. You would determine the fanning friction factor for the pipe length. You would determine the total K sub F, which is called the excess head loss, by summing the contributions from the pipe fittings, entrances, and exits. Use this to solve for big F, and we'll recall that big F is a function of the velocity, which, just to refresh our memory, remember this is our term for F. So this is what it means. F is a function of the average velocity. We then solve the mechanical energy balance. If we find something that is satisfied, you guessed an average velocity that was correct. If not, iterate. Now, if this sounds suspicious to you, you are absolutely right. If you do the guess and check method, it is very unlikely that you're going to guess a correct velocity. So to avoid the frustration of having to guess and then check and guess and check and guess and check, you can set up a system of equations. That would be a much smarter way to do it, I would think. And then finally, what you would do is you would solve for the mass flow rate. That is equal to the density times the average velocity times the area. Once again, the way I like to think about this is the velocity times the area is the volumetric flow rate, and multiplying by the density converts that volumetric flow rate into a mass flow rate. So let's look at this example. Water is contaminated with a small amount of hazardous waste, and that is being gravity drained out of a large storage tank through a straight new commercial steel pipe with an inner diameter of 100 millimeters. Open gate valve in the pipeline near the tank, and the whole assembly is horizontal. The liquid level is 5.8 meters above the pipe outlet, and the pipe is severed 33 meters away from the tank. What is the mass flow rate of the material escaping? So let's go through the steps that I just outlined. Step number one is that the problem says that we have one gate valve, which is there in my diagram, and 33 meters of commercial steel pipe. Now, it does not matter where the gate valve is. So if this length is 10 meters and this is 23, for example, or if this is 20 and this is 13, it's all going to be treated the same. Fluid properties are that of water because we've got water that's contaminated with a hazardous waste. So overall, the fluid properties are going to be the same. And then we won't forget there's a pipe entrance here and a pipe exit there. So 0.1, we will pick as the upper interface of the tank. And I'm doing that because I know what the pressure is at that point. And pipe 2, like I said, will be the pipe exit where we have material that is exiting. So we'll determine the parameters that we have. P1, we chose this point because I know the pressure there is atmospheric. It does say open tank somewhere in the problem statement. So that's what clues me in for that. 0.2 is going to be discharged to the atmosphere, so atmospheric pressure there as well. We'll apply this approximation that the velocity there, although the liquid level is draining, that the velocity is 0 at this point, and the velocity here is what we want to solve for, so we don't know what that is quite yet. Z1, the initial height is 5.8 meters above the pipe outlet, so that's our first height value. And then it doesn't matter where we put the Z. All that's important is that Z1 minus Z2 is minus 5.8 meters. Pay attention, by the way, to the signs of these things. It's very easy to overlook a negative when you do this sort of thing. Yeah, G over GC times delta Z plus F is equal to 0. And that comes about because the other terms of the mechanical energy balance have canceled. I didn't explicitly say this time, but worth noting again that on the right-hand side, you would have shaft work. There is no shaft work here, so that's why it equals 0. Now, the problem is figuring out what F is, this frictional loss. Now, you might say, why don't we just assume that friction is 0, and that would be the worst case scenario? And that's a bit of a flawed. I mean, you want to assume the worst case scenario, but you don't want to be totally unrealistic. So if you were still, before you've taken fluids and you didn't have the ability to calculate F, this would be a good first approximation as determining the absolute worst case. But in order to be a little bit more realistic, we should calculate this F. All right, so the excess head losses, we've got this expression that we've talked about before. We have a pipe entrance, which we have the value for KF. We've got a gate valve. So you go to table 4.2 and you find these values for the gate valve. You've got a pipe length. 33 meters is what you plug in. The diameter of the pipe was also given. It's okay here that I'm working in meters. So the units are going to cancel. A little bit later on, we'll have to convert to inches. We'll see exactly where that is. Now, we don't know what f is, little f is quite yet. So I'm leaving that in the equation for now. So I've just simplified this by doing the math on everything else. For a pipe exit, we've got KF is equal to 1. And if I sum these all up, I get this following expression. So I can't lump terms with a little f and with divided by RE, but I'm going to keep this for now. And then we'll assume that the Reynolds number is large. So it may seem silly to work this all out, but again, hopefully it's always start but from first principles and then cancel as necessary. This is going to simplify things greatly because I'm going to drop this term completely out. So I'm just left with this. We're going to solve for f now. So f is equal to a sum of all the kf's, which is this, times the average velocity squared over 2gc. Everything I've been doing so far is in SI units, which simplifies the GC. That is equal to 1. Remember, that's Newton over meters per second squared. And then if I plug in the expression for KF, I'm left with what we've got. I've also divided by 2 there. So F is a function of the Reynolds number and the pipe characteristics, remember. So I need to figure out what that Reynolds number is. I do that by multiplying the density times the average velocity times the characteristic length, which in this case is the pipe diameter, all divided by mu. This is the viscosity of water, which I had to look up. And I obtain that my Reynolds number is 1 times 10 to the 5th times the average velocity. Now, whatever the average velocity is, unless it's super, super small, we're going to go back and check this later. But 1 times 10 to the 5th is a large number. So this seems like sufficient. This lets me know I'm on the right track when I neglected Reynolds number up here. Unless velocity ends up being something super, super low, then I'm justified in saying that Reynolds number is large. So table 4.1, I'll look up the roughness of new commercial steel pipe. I will obtain that the roughness is 0.046 millimeters. My diameter is, again, 0.1 meters or 100 millimeters. I do have to convert the units to be consistent with one another. They're going to cancel. This epsilon over d term should be dimensionless, so that all is looking good. And I plug everything into my 1 over square root of the friction factor equation. Go all the way back to the mechanical energy balance. I now have a term for big F. I'm going to throw that in and notice that I'm going to have, I now have one equation for one unknown, which is the exit velocity, this average velocity squared that I have to solve for. So I lump things together. You should pause the video now and make sure that you understand the algebra that I'm doing. But I can simplify it and get that. I get an expression for the average velocity, and it's in terms of the friction factor F. But this is a fundamental issue, right? Remember, the average velocity depends on friction factor, and if I look up what the friction factor is, it depends on average velocity. So what I would recommend is going on Excel and making an initial guess for F using figure 4.7. Use that F to calculate average velocity. And again, this is where you would use that table or you would use the equation. I will personally tell you, I would tend to use the equation because that's less, figuring out that I have to do. I would then goal seek the value of F and the corresponding average velocity to solve for the Colebrook equation. And this is the answer that you should have gotten. Going all the way back to what I'm asked to calculate in this problem is the flow rate of the escaping material, which is, again, the density times the average velocity times the area. This is the area of the whatever it's escaping through. So because the pipe is sheared off, this is going to be a circle of diameter 0.1 meters. So let's plug in numbers again with my value for velocity that I found. Oh, and it's also worth noting, by the way, that if velocity is 3.8 meters per second, just to circle back, so 3.8 times 10 to the 5th, that is a large Reynolds number. So I'm all good there. So plugging in values and crunching the numbers, density of water is 1,000 kilograms per meter cubed. Plugging in my velocity of 3.8 meters per second, and then pi r squared is going to be the area where my radius is in meters. I get 30, and let's just quickly double check my units. So meters and meters squared are going to cancel with meters cubed. I'm left with kilograms per second, which is indeed a mass flow rate. And that is the problem solved. So that's going to be all for this video. Thanks for watching. See you next time.